Welcome. Today we are going to delve into the concept of the Multilevel Feedback Queue, or MLFQ. It is a sophisticated scheduling algorithm used in operating systems. The Multilevel Feedback Queue is all about dynamically adjusting process priority based on process behavior. So, what exactly is a multilevel feedback queue? It's a scheduling algorithm that uses multiple queues, each with a different priority level. The key is that processes can move between these queues. The priority of a process changes based on its CPU burst behavior. This system favors input-output bound and interactive processes, giving them quicker response times, and it penalizes CPU-bound processes, preventing them from monopolizing the CPU. Now let's explore the core principles of how multilevel feedback queue works. First, new processes always start in the highest priority queue, ensuring they get quick initial access to the CPU. If a process uses its entire time quantum, meaning it consumes all the CPU time allocated to it in a given queue, it moves down one level to a lower priority queue. However, if a process gives up the CPU before its time quantum expires, typically because it's waiting for an input-output operation, it stays at the same priority level. Finally, to prevent starvation after a certain time period, all processes are moved back to the top queue. This is known as a priority boost. Let's focus on the concept of the time quantum in multilevel feedback queue. Each queue is assigned a different time quantum. This is the amount of time a process gets to run on the CPU before it might be moved to a different queue. For example, Q0, which has the highest priority, might have a time quantum of 8 milliseconds. Q1, with medium priority, could have a 16 millisecond quantum. Q2, at a low priority, might have 32 milliseconds, and Q3, with the lowest priority, could have 64 milliseconds. Here's an example of process behavior. Process 1 starts in Q0 and uses CPU in bursts. Process 1 uses the full quantum in Q0, moves to Q1, then requests input-output before using the full quantum in Q1, so it stays in Q1. Now let's discuss the priority boost mechanism in multilevel feedback queue. Why is it important? It prevents starvation of long-running processes, ensuring they eventually get a chance to run at a high priority. It gives every process a chance to run at the highest priority, preventing any single process from dominating the CPU. It allows the scheduler to adapt to changing process behavior. It handles cases where CPU-bound processes suddenly become interactive and need quicker response times. Typically, all processes are moved to the highest priority queue after a fixed time interval, for example 100 milliseconds or 1 second, regardless of their current queue level. Let's examine how different types of processes behave under multilevel feedback queue scheduling. First, input-output bound processes use the CPU in short bursts, then yield it for input-output operations. Because of this, they tend to stay in higher priority queues, getting quick response times. CPU-bound processes, on the other hand, use the CPU for long periods without yielding. These processes tend to move down to lower priority queues as they use up their time quantum. Finally, some processes may exhibit mixed behavior, changing over time. Multilevel feedback queue adapts to this by moving them between queues based on their recent CPU usage patterns. The CPU burst length for input-output bound processes is short, while for CPU-bound processes it is long. Input-output bound processes typically reside in higher queues 0 and 1, while CPU-bound processes end up in lower queues 2 and 3. The response time for input-output bound processes is fast, while it's slower for CPU-bound processes. Input-output bound processes rarely use the full time quantum, while CPU-bound processes often use their full time quantum. Priority boost has a minimal effect on input-output bound processes, but a significant effect on CPU-bound processes. Let's take a look at a simplified multilevel feedback queue scheduler, using pseudocode to understand how it might be implemented. Here is a basic structure for a multilevel feedback queue. This includes the priority, time quantum, and the processes associated with the queue. This is the main scheduling function, which iterates through the queues and returns the process with the highest priority. Now, let's look at how process completion and priority adjustments are handled in our multilevel feedback queue implementation. This function is called when a process completes its time quantum. If the current queue is not the lowest priority queue, the process is moved to the next lower priority queue. Otherwise, it is requeued in the same queue. The function process yields CPU is called when a process yields the CPU before using its full quantum. In this case, the process remains at the same priority level. Let's discuss the advantages and limitations of using the multilevel feedback queue scheduling algorithm. Among the advantages, multilevel feedback queue is responsive for interactive processes, providing them with quick turnaround. It adapts to changing process behavior, ensuring that the scheduling remains efficient. It balances CPU and input-output bound processes, preventing one type from dominating the CPU. It prevents starvation through its priority boost mechanism, and it does not need prior knowledge of process behavior, making it flexible. However, there are also limitations. Multilevel feedback queue is more complex to implement than simpler scheduling algorithms. Its performance depends heavily on parameter tuning, which can be challenging. There is a potential for gaming the scheduler if processes are designed to exploit the algorithm. There is overhead from the frequent priority adjustments, and it may not be optimal for all workloads. In summary, multilevel feedback queue scheduling dynamically adjusts process priorities based on observed behavior, balancing responsiveness for interactive processes with throughput for CPU-bound tasks. The three main characteristics are: adaptive, it adjusts to process behavior without prior knowledge; fair, it prevents starvation with a priority boost mechanism; and responsive, it favors interactive and input-output bound processes. If you like this video, hit that like button and don't forget to subscribe. Visit codelucky.com for more such useful content.